I'm going to speak about the finite Hilbert transform. This is a joint work with two colleagues of mine, Susumu Okada from the University of Tasmania in Australia, and Werner Ricker from Germany. I will abbreviate this work by Curbera Okada Ricker COR. Okay, this is a short outline. I will speak about the finite Hilbert transform. What do I mean by that? What happens in rearrangement in vertical space? Inversion of the finite Hilbert transform, which is a classical problem, the spectrum, and the final thing about this operator in a particular space, which is the sequence space L log. So what is the finite Hilbert transform? Well, we are working in the interval -1, 1 all the time. So this is not the real Hilbert transform, which is the full line. And this is an operator defined by a principal value. We integrate the function fx with this kernel. This operator can be shown to be meaningful for every function in L1. This operator is related to a famous equation, which is the airfoil equation. In the origins of aerodynamics in the 1920s, the problem of supporting a plane, why does a plane fly, was related to the airfoil equation. What is the shape of the wing to support? Inverting this operator, which is solving the airfoil equation, was the solution to this. Related to this, there's a famous result of Marcel-Ries, which says that the Hilbert transform on the full line, it maps LP into LP when P is strictly between 1 and 3. This result can be extended to the restricted, to the finite Hilbert transform when between LP and P in -1, 1. So that this operator is bounded precisely when P is between 1 and 3. This allows to study the classical LP theory for this operator. This was developed by many authors. There are mainly two groups. One is a group, let's say, in Western Europe. Was Schongen, a German mathematician, Tricomi, in 1950, Widom, and Jorgens. A similar theory from a different viewpoint was developed by the Soviet school of one-dimensional singular integrals. There are very important names: Luchava, Gakov, Goldberg, Hedadelice, Krupnik, Mifflin, Mushakishvili, and Beckwith. Mainly, in particular, the Georgian school studied this intensively. So, the LP theory is a classical theory which has been developed by many mathematicians from two different viewpoints, arriving at very clear, clean, and definite results. We're going to change from the LP theory to a different family of spaces. Why? The problem is, why do we change? So, a rearrangement by the space, which is the same thing as Sergei is asking as defining a symmetric space, almost like the same theory. But if we make a general definition, would be a function space where the norm, and hence membership of a function, does not depend on the shape of the graph, just on the size. So no matter how the graph is, the only important thing is how big is the graph. That determines membership and norm. That is a rearrangement by the space. In this case, simple drawing, these three functions have different shape. But if I measure the size, if I take how big is the set where they're bigger than this, measure the same. So that these three functions belong at the same time to all of the spaces. Because from the viewpoint of rearrangement invariant, they are the same function. That is the idea of symmetry. This family is very interesting for analysis because it contains the classical LP spaces, weak LP spaces, Orlich spaces, Lorentz LPQ, Lorentz lambda spaces, Martin spaces, and so on. Many spaces which arrive solving problems in analysis are covered by this very important. Okay. There was a very important theorem, I think it's 1967 of Boyd, which studied when the Hilbert transform on the full real line maps rearrangement invariant space X into X. And then Boyd showed that this, remember that if we had here LP, this was P between 1 and infinity space. Now, in this case, is these two indices have to be strictly larger than 0 and smaller than 1 space. But these two indices are very important for many applications and are called the Boyd indices space. They are very technical. The important thing is the idea. What they do, they measure in a space X what is the effect of dilating the function. When I have a function and I expand the function, the same shape but expanding, the norm changes. How? So this is what happened in an LP space. I'm computing an LP norm and I get my function and I dilate by t. I do a change of variable and the effect is this. Dilation is this. This is dilation. Then I forget about the t and I look at the 1/3. That is the index. So this is what I can do in a general space. So Boyd's result, this very important result, translates into -1, 1. And if then X is a rearrangement of space in -1, 1, then T, our finite Hilbert transform, maps X into X precisely when the same condition. When this is R for state. Okay. Now we know when this happens. Question. General question in mathematics. Why do we change the problem to a more general problem? One needs a justification. Why? And the answer, because LP is inside rearrangement variant. Why do we, an LP theory has been studied for finite Hilbert transform with success. Why do we continue studying in a larger space? Maybe because we get more knowledge. That is the good reason. Not because we generalize, just because we get more knowledge. And this is the explanation why. In the 1960s, Harold Whedon, American mathematician, he studied the finite spectra of the finite Hilbert transform from LP into LP. And he studied perfectly, with full detail, define not only the spectrum, but the classification of the spectrum. Okay. Now, it turns out now that we change LP to X. This is a result of Curbera or Cadaveric. Where with this condition, T maps X into X. Now, the following happens. The point spectrum is empty when, if and only if, this Lorentz space is inside X. The residual spectrum is not empty, if and only if X is inside this other different Lorentz space. And the continuous spectrum equals the full spectrum when X doesn't contain neither this space nor this space. This means that in order to understand this operator, it's important to situate yourself in the scale of rearrangement by spaces, because this is not an empty space. So the explanation for the spectrum disappears if you don't look somehow in analysis, symmetric spaces or rearrangement of spaces is like putting a glass that allows you to see finer. So for a spectrum, you need this glass. Without this glass, you don't understand what happens. The reason is precisely this space. So this is the justification for studying in rearrangement by spaces. The operator is explained in more detail, fully. So let's go to the famous problem of inversion. Critical thing in this operator is this function which is related to the arc sign density. W of x square root of 1 minus x squared. And then this result is known, I think, already. Maybe the beginning of the result goes back to the 1940s by Hilbert, an important Georgian mathematician. If I'm LP, so t between 1 and 2 strictly, then given any function g, I can find another function f, which is the solution for the equation. This is inverting the operator. So if you give me g, I build up this and I find an f. This is a perfect solution to the problem in this range. There's no unique solution because it depends on an arbitrary constant. What happens on the other side when p is larger than 2? Then there's not always solution. If g has to satisfy this condition. If g satisfies the condition, then therefore equation can be solved and there's a unique solution. This theorem as it holds took a long time to establish all the cases, but we could say that by 1972 was finished. It was completely understood, this inversion. Now we want to understand this theorem in the finer scale of rearrangement line spaces. There are more spaces, finer results. So we start with the space X. This is the previous LP, but now we have more general. And remember that the boundedness of T on X depended on these void indices. And now we separate from 1/2 to 1. This corresponds to P between 1 and 2, 1.5 and 2. We have the same solution. Given an X, there's a function such that the solution is this. It's the same result for LP, but for a tremendously large class of spaces. In the other case of the index, between 0 and 1/2, again, not always the solution. The solution depends on this condition, but if you have that condition, then there's a unique solution. This extends completely the previous result. There's something very interesting here. L2 is not covering this thing. Neither L2, neither of these spaces that were very relevant for a spectrum, L2(1) or L2(3). Somehow, in contrast with, I can say that I think that almost all operators that I know, their behavior in L2 is not understood, because in general we do have the opposite. On privileged space, operators are understood, well worked, and easy to control. And then difficulties come when we go away from L2. Here's the opposite. There's no inversion theory for L2. Still, there's no inversion theory for L2. It was no inversion theory in the LP case, in the LP theory, but now there's no L2, even in the spaces which are close to L2. Again, there's a gap of blindness. We have no idea how to invert the operator. That remains a big problem. Okay, let's take a look at the spectrum. This is the solution of the spectrum that was given by Guido in 1960. 1P, I take a P between 1 and 2. I build up this set of complex numbers. I have to add 1 and minus 1, and it's designed by this, the argument of this quotient. And if I draw, I have the union of these two circles. This is the set RP. Duality, P and P conjugate, shows that these two are the same, these two sets. Okay, we don't prove this theorem, which was perfect. This is the LP theory, P between 1 and infinity, the operator mapping LP into LP, and then first, the spectrum is the set RP that I just drew. Perfect. Now, find a spectrum, point, residual, and continuous spectrum. P between 1 and 2. Point spectrum is the interior. Residual spectrum empty. Continuous the boundary of that shape. P equals to no point spectrum, no residual spectrum, only residual spectrum, which is the segment minus 1, 1 close. P between 2 and infinity. Empty interior boundary. This term is beautiful and sharp. 1960 with. Okay. Now, we want to study a spectrum, but now we have X, not LP. Any rearrangement invariant X with this condition, so that maps the X into X. And we need two indices. This is, well, this is, I should apologize because this can be written down in a simpler way, and I have not done. But let's say some range of P's which satisfies some condition. But allowing this index, which is that if you give me an X, I can find this number. Then we have a result, because if Px is larger than 2 or is equal and is attained, because this is an infinite can be a minimum or not. In these conditions, point spectrum is empty. Out. If P is smaller or equal than 2 and is attained, then point spectrum is the same shape that we had before, but we have to take out the 2 points, 1 and 9. And if P is strictly less than 2 and is not attained, then point spectrum is the infinite. So point spectrum is finished. We have understood perfectly point spectrum. For this general operator, on this very general spaces, only determining this, which is called the inclusion index, gives a full solution to the point spectrum. Now we go to the residual spectrum. Again, non-trivial Boy indices to have this boundedness. Now I look to the other side, which is I find the supreme of all Q's such that X is inside the space LQ1. That gives me an index, a number. And now we have, if QX is larger than 2 and is not attained, we call that as a supreme, then residual spectrum is the interior of the shape. If Q is larger than or equal to 2 and is attained, then residual spectrum is the boundary, I mean the full thing, but for the point 1 and minus 1, so that to be out. And if QH is smaller than 2 or is 2 and is not attained, then there is no residual spectrum. Again, this index classifies in full the spectrum. So we have point spectrum and residual spectrum completely determined by a number that measures how your X is situated in the LP scale. What is the problem for having the full spectrum that we have continuously? Continuous spectrum is always, or this is my understanding, a delicate part of the operator. It's very much difficult to study continuous spectrum. So, regarding continuous spectrum, the identification of continuous spectrum is in general complicated, no? We were able to prove this. I'll explain this but with a lot of effort. The only thing that we can say, so then, a spectrum can be classified in three parts. One way, three parts: point spectrum, residual spectrum. The two first are completely determined by an index. The third one is we have not been able. The only thing is that we can, in any case, in a general situation, the spectrum we can put inside. Remember this were like two circles, the union of those two sets, but not precision. In this proof requires tools from interpolation. Somehow this is why it's not refined, because interpolating, you're not speaking about one operator, but about many operators at the same time. It's not sharps, the two. What is true is that in the particular case in which the Voynich indices are the same, which is a very particular case, then we can answer the full, because this part is we know always. This part we know, and this part is the difficult part. When we have this condition, we can complete everything. So in that case, we have to send the Williams result to any rearrangement by space, but this restriction is very strong. Just to exhibit some example, Lorentz spaces are like orange, like LT spaces, but with a second index that allows to be half a finer scale. So when P is between 1 infinity, and we are not putting R because the space is not separable, I'll label T, PR, the operator mapping that. Then in this case, again, we can give a full solution to the expression of the space. Mainly because we are in the part in the previous theorem. So there are many situations in which our previous theorem covers the full spectrum, but from the theoretical point of view, we are lacking really the understanding of the continuous space. And let me just finish with the Sigmund space. What is this? Well, the Sigmund space, I mean, we classify integrable functions by how they grow. And an important space is this one in which we require a function that is integrable, but also when we multiply by the positive part of the log of the function. This gives a space which is smaller than L1, not all functions are like that, but the space is larger than any LP, or PB is certainly larger than 1. All LPs are inside here. The space is number 1. Also, all the spaces that I spoke before, all symmetric spaces with non-trivial indices are inside here. So somehow this space, before Sergei Staskin spoke about the spaces of Lx of exponential integrability very close to infinity. Now I am in the other side, I'm very close to L1. Very, very close, because all the LPs are inside, but this space is not an LP and it's not in the full. The question is, can we do something? Can we understand the operator, the finite Hilbert transform in this space? Because the space does not act in L1, so we cannot get to L1. What can we say there? So this is the attempt is to understand in a very large space. Well, the first thing is that P maps L log L into L1. That's also bounded. And in the theory of the finite Hilbert transform, a very important tool is the Poincaré-Bert transform. It's a critical formula that goes back to Hardy. Hardy in the 1910s was trying to study if one is able to permute two principal values. What happens, under which conditions principal value is a principal value is the reverse order. That is a non-trivial problem. At the end, solution came and has taken time, but there's a result of Bertrand, Poincaré, so many people have contributed, and it's a point-wise inequality. Here's where we have to, because T of F, T of G, there are two principal values multiplied of G, but here we are applying two successive principal values, and that is the delicate one. So this inequality is very important. This was proof for LPs. It has had a long process. The latest solution, the final solution in the LP theory was in 1972, a British mathematician called Love, that he proved that this worked for LP and LP dash, conjugated exponents. Before, it was not even clear that. Okay, what we do in this result is that we extend this result to allow functions in L log L. We need a Poincaré-Bertrand formula in L log L to try to invert the operator. And the main difficulty was that the Poincaré-Bertrand does not hold, because Poincaré-Bertrand only is here. And we are here. We are beyond. So first we had to prove a Poincaré-Bertrand formula, and we did. Now with this Poincaré-Bertrand formula, this operator is not invertible because it's not injective. But this is a perform operator, so this is pseudo inverse. I think this really goes back to Hilbert's, in fact, the formulation of this. So this is, so I was right. Hilbert proved that this operator maps LP into LP. And this result is a classical result that one can see in the book of Krupnik, and so the proof is very classical. But in order to go to L log L, because remember, let me go back for a second, is that everything that happens here is infinitely away from here. This space is too far away from here. So if we have things occurring here, we cannot reach there. Truth does not flow there. So the point is, the result of Hilbert tells you that this operator is from LP, but that says nothing to L log L. How do we do this? We're going to use extrapolation, which is a very important thing. No? For extrapolation, we need not only that it's bounded, we need that to have a bound on the norm, a concrete bound on the norm. When in this case, when we are near one, P is near one. Then the strategy, which really comes from the ideas of Hilbert, is to study T plus T hat. And then, well, this is just technical. One requires, in order to find this norm, a very fine analysis of all the constants appearing in the computation. It's not deep, but it's delicate. It's very delicate to find the right bounds and parameters to get the right thing. At the end, we find this. This is the critical thing. This operator, which from Hilbert we only knew that it was bounded, full stop. We know that it's bounded, and that it's bounded by a constant divided by P minus pi. That is perfect. Because this shows why it's not bounded in L1, because when P is 1 blows up, and as you get to close, L1 goes up. But this is the necessary bound to apply a very important theorem, which is Janos extrapolation theorem. Janos extrapolation theorem says, if you have an operator which has a P minus 1 down here, then you can jump to L log. That is the critical. Then applying that result, well, I formulated here more general, but the idea is, thanks to this bound, we can, this T hat goes from L log L to L. That is the important. With that, we can, well, this is just a drawing how this operator goes from all the, this is a sequence of a scale of spaces related to L log. No, but this is not related. With this, we can do a sort of inversion for L log. And it would be, when we identify the range, which is those functions in L1, with the pseudo inverse map goes to L log L, and T hat is G. That is the range. And then if we have a function in the range, then the solution goes, or the for equation is exactly as this. So this solution which existed for LPs between 1 and 2 can be extended to L log L. Remains the same expression. Applied where? To a different class. The problem of this result is that the class is not independently identical. That is the problem. At least we are able to see that L log L square, which is a big space inside here. So for every function here, we do have distance. So this is not a full inversion theorem, but it's a first attempt and rather neat. Okay, all this study beyond the LP theory. We studied here in this result, this paper in 2019, inversion and extension of Hilbert transform -1. We have had a series of papers. This is the paper of the spectra, where we almost got the full spectra, and the last part in Sigmund space is about Curbera. So, thank you.